shall we go ahead and get started? What do you think, Susan, Sarah?
Yeah, just fine on this end.
Okay.
This is Sarah. I'm going to welcome everyone to the first NAVIS webinar. I'll go ahead and get started. Thank you all for joining us. Before we do get started, I have a few sort of logistical notes. You sort of probably heard us shout. During conference, please keep your microphones muted. There's a little microphone to the left of your name, and that'll just help keep feedback down and help keep the line quiet for everyone to hear. If you have any particular questions during the presentation, you can use the chat function, which is below the list of participant names, and send in questions, and we'll address those at the end of the talk. You can also raise your hand, which is also to the right of your name, but I think the chat function will help sort of keep questions order and keep organized. Come back to after the presentation. With that, I think those are all of the notes I have, and I will turn it over to Fiamma to introduce NAVIS.
Great. Thank you, Sarah. And so welcome to everybody. So wait, Sarah, does this mean now I have control of the slides?
Well, momentarily, yes.
So I can keep going. So this is the first webinar, hopefully, of a series that we'll be putting together. And so I just wanted, I won't take too much time. So NAVIS is a virtual institute, and it's focused on the North Atlantic, its circulation, and in particular its connection with AMOC. And if you're wondering how it came about, NAVIS was sort of conceived in conjunction with a large international observational program, OSNAP, which I think many of you have heard of and many of you are part of. And the goal of NAVIS is really to act as a link between some of these very large observational programs that are going on in the North Atlantic, such as RAPID, Vitals in Canada, and NACLIM, and but also modeling efforts. And the idea was just to create an institute that would facilitate interaction amongst the different groups. And we're just getting started. We've had some seed funding from NSF, which will cover NAVIS for minimal administrative activities for a few years. And we have a steering group, which is listed in the slide that you can see, and it's an international steering group. We also have a list of PIs that have adhered to be NAVIS PIs, and they're listed on the website, and many of them are either your advisors or people you work with at your various groups. And what you're getting involved in is the NAVIS early career effort, which is essentially trying to do all of the same things as NAVIS, but it's really aimed at junior people, graduate students, postdocs, assistant professors or scientists within a few years of receiving their PhD. And the hope is that we will really create a community of people who are excited about their research in the North Atlantic and who can benefit from interacting. And on the slide that's up now, I've outlined sort of 5 of the things that as the steering committee we've discussed doing. Some are happening already. And so this webinar series, the idea is that it'll be a series of by experts, but also tutorials on methodologies, and it will span across different themes, from how to observe the AMOC to what are its impacts, the AMOC in models. And so we are putting the series together. You can expect roughly 1 webinar a month, and Susan kindly agreed to give the first one, and will be recorded, so if you miss it, you'll have a chance to click on the video. It'll go off of the website. And what else to say about the webinars? I think it. We also are planning get-togethers. These will be informals, just get to know each other at some of the science meetings. There has been one already for the EGU meeting, and you'll be getting emails about getting together at IUGG if anybody's going, and then at the AMOC meeting in Bristol, and so on. We are also planning a half-day workshop to physically get together preceding the Ocean Sciences meeting next year. And then we have some idea about how to foster interactions. The early career group is somewhere on the order of 30 people, and so it's a pretty big group, and we'd like you to interact. So we have some ideas about doing blogs and also facilitating visits and internships at partner institutions, and this is all getting going. So we do really value your feedback, and at the end of this webinar, you will be receiving a survey that essentially asks what might work, what you think might be a good idea, and so I'm going to ask you to save comments on NAVIS as well as the webinar series. There's room in the survey to give us input, and so that we can really gear it towards what the needs of this community are. And that's it. So I'm going to welcome everybody, and I'm going to pass it on to Susan.
Fiona. A short introduction for those of you who don't know me. I'm Susan Lozier. I'm a professor at Duke University. And I believe I was asked to give this first webinar because I have been leading the international program OSNAP. And so today I'm going to start with a broader review of overturning in the North Atlantic, but in large part, this review leads to our motivation for the OSNAP program, which was initiated last summer. We deployed the program last summer, so I'll get to that near the end of my talk. So Sarah, I have lost my, for moving forward.
Hello? Bring it back up. It appeared on mine as well.
That's the screen too.
Okay. Seminar I was at Hui one time where the power went out, and the seminar speaker had no slides, and so he proceeded to give the whole thing on the chalkboard. Do not have that opportunity.
Let's hope it's not necessary.
Okay. I'll wait till they come back.
I have slides back. Click on this.
I've got it. Okay, thank you. Okay. So I'm going to, as I mentioned, I'm going to give a broad and very quick, review of the overturning the North Atlantic. Do I have control now? Okay, great. All right. So almost a century ago, some of the first full hydrographic sections were taken of the North Atlantic as part of the German Atlantic expedition. And this gave one of the first views of the overturning circulation via the properties. So in this section along 30 west of the salinity, we can see the North Atlantic deep waters penetrating, into the rest of the North Atlantic. And so over the following decades, many trans-basin cross-sections were taken of the property fields. And physical oceanographers were very interested in tracing these water masses and understanding how the movement of these water masses really impacted the transport of heat and salt, through the basin. And then a decade ago, the importance of this overturning circulation extended beyond just the transport of heat and fresh water and mass into trying to understand the transport of the anthropogenic CO2 in the deep ocean. Many of you may be familiar with this, but this is from Chris Sabine and all colleagues who put together this cross-section through the North Pacific, across the Southern Ocean, and up Atlantic. Actually, from zero is from Iceland. Down, if you're moving to the right across the x-axis in distance, it ends up at the Aleutians. But what this shows is the penetration of the anthropogenic carbon dioxide into the deep ocean in that North Atlantic. And so just how decades before we saw the penetration of tritium and helium-3 in the deep ocean from the geosex cruises, Sabine and al. College are showing how the penetration of CO2 now shows up in the North Atlantic, and we understand this to be because of the overturning circulation in the North Atlantic. So about this time in 2004, not only were we seeing this picture of the penetration of the anthropogenic CO2, but this was also about the time where there was a real concern about the possibility of abrupt climate change. So a few years before, a study came out that was looking at the synchronous changes in the atmospheric temperatures recorded by the ice sheets in both Antarctica and Greenland, and the study showed or suggested that there were abrupt changes in atmospheric temperature that were global, that occurred on the order of years to decades. So there was a concern in the late 90s, early 2000s about abrupt climate change. This was sort of the time period then where the distance between what the paleoceanographers were studying and physical oceanographers were studying, really that remove really collapsed, and there was a strong focus then on the overturning circulation, because the suggested change for those abrupt climate changes, climate change in the atmospheric temperatures, the suggested cause was the overturning circulation. So at about that time, the conveyor belt paradigm, things started to shift. Instead of talking about the conveyor belt, Carl Wunsch suggested that we should talk about the meridional overturning circulation because it had a mathematical construct instead of the conveyor belt. We also started talking about this MOC and understanding that it could be both have some wind-forced components as well as driven components, and so the term thermohaline circulation started to go out of vogue as well to describe this overturning circulation. So about a decade ago, into our lexicon was the term MOC, and then for the Atlantic component, the AMOC. So now we had a mathematical construct instead of referring to this overturning as the conveyor belt. However, a decade ago, we still were under many assumptions about the old conveyor belt paradigm that was promoted primarily by brokers studying the paleoclimate. Many of those same assumptions were carried over to the MOC. And what I want to talk about in this overview are some of those assumptions. First assumption that was made about the overturning was that the overturning could be estimated from a synoptic measure of the full depth transbasin density field. We had an assumption that the lower limb of this overturning circulation was carried along deep western boundary currents, that the upper limb was carried in the near surface subtropical waters via the Gulf Stream and North Atlantic Current. An assumption that the temporal variability overturning was spatially coherent. And the last point is the one I'll get to that really is the lead up to OSNAP. There has been, and still currently, an assumption that the transport and property variability of the AMOC results in large part from the change in the transport and property variability of the deep North Atlantic water masses. So I'm going to step through each of these assumptions, some a little more quickly than others, because presumably you have all heard various people talk about a number of these. So many of you, I think, on the call are familiar and are intimately involved with the RAPID program. And so the RAPID program in existence since 2004 has been really instrumental in changing our understanding about the temporal variability of the EMOC. So this is an array that's at 26 north in the North Atlantic, and this is the schematic showing the instrumental design with the cable measurements through Florida Straits, the dynamic height moorings across the basin, and this is coupled then with wind estimates from satellite measures. So when some of you as early career scientists may not appreciate this, but when Stuart Cunningham and all colleagues put out in 2007 the time series from that first year, this was really, I think, a big impact on the field. I know it really changed my mind completely about what to expect about the overturning. So prior to this, a paper that was published in 2005 had reported a slowdown of 30% over 5 decades in the over-circulation measured at 26.5 degrees north. And then in this, you can see the, in this time series, red, the overturning is the sum of the Florida Straits transport, the upper mid-ocean transport, and the Ekman transport. And this overturning in the course of a year had a 6-fold change. And so we were able really then to understand that those synoptic measures over 5 decades could not really be representative of the annual changes because of this strong intra-seasonal variability in the overturning. So the work at RAPID has continued. This is from McCarthy et al. 2012. It was just recently updated in a Progress in Oceanography Review article that was published just earlier this year. And this is showing again all of the different components that together make up the overturning circulation, which again is in red. It's now showing it over the 7 years of data. And recently, Eleanor Frocka-Williams, just a few months ago, a paper appeared in GRL where she used satellite altimetry data along with cable measurements and then extended the record at 26 north back to 1993 and shows that over that time period, there's been about a 1 sphere decline. I think it's safe to say that people are not sure if this is a long-term trend or part of the decadal variability. And so it's has been very important for these measurements to continue. RAPID has given us, I think everybody understands this, has given us understanding not just about the change in these of the overturning, but also just what's responsible for the seasonal variability, intraseasonal variability as well. So it's been really radically changed, I think, our view of the expectations we have on the overturning in terms of its temporal variability. So the second assumption that I want to talk about is the one about the lower limb. So this is a schematic showing in the warm colors our expectations for the surface currents, and then in the blue and purple showing what we have believe be the pathways for Iceland-Scotland overflow water, Denmark Strait overflow water flowing over the Greenland-Scotland Ridge, moving cyclonically around the deep western boundary current. So starting in the late 50s and early 60s, you know, Henry Stommel and colleagues had a theory of the deep western boundary current that was largely based on large-scale potential vorticity dynamics, and the argument for these deep western boundary currents went predicated on the assumption that if there's a mass source into the North Atlantic at depth, there needs to be an upwelling, a general upwelling of those waters into the near surface waters. That upwelling would produce a stretching that would induce potential vorticity, and to offset that in steady state, then there needed to be a poleward flow of the waters in the interior in order to maintain a steady potential vorticity balance. So if everywhere there was a poleward interior flow, then the deep western boundary currents needed to be the place where we have for continuity, or where we could satisfy continuity. So after someone had this theory, many people went out and measured in the deep western boundary currents and indeed found that they were conduits for the high latitude water masses, and you measured transport and measured properties. So for decades, they were considered the conduit for these water masses. But there were some hints from tracers and from palace floats that their deep western boundary current may not be the sole conduit. And so this prompted Amy Bauer and I about a decade ago to propose to NSF an export pathways program. And so this program, that proposal was funded, and in 2003 and 2006, we went up into the Labrador Sea along this Bonavista line that is similarly led by the Atlantic Zone Monitoring program out of the North Atlantic Fisheries Center in Canada, and we released over 70 floats over a period of 3 years. Every 3 months, we released 6 floats, 3 at a depth of 700 meters and 3 at a depth of 1,500 meters. And the purpose was to release these RAFOS floats directly in the deep western boundary current at the depth of the Labrador seawater and to track their pathway toward the tropical gyre. These floats were acoustically tracked by moored sound sources, and at the end of 2 years, they were released. They released their anchors, they popped to the surface, and they relayed their information to a satellite. The analysis of these floats, which you see on the left-hand side of your figure there, these dots up off the Newfoundland coast show where the floats were released. And this is a spaghetti diagram showing the 2-year trajectories of these floats. The curves indicate the temperature anomaly, which is the final temperature minus the initial temperature. What you see is that of those floats that move from the deep western boundary current in the subpolar gyre southward into the subtropical gyre, the majority of those are moving via interior pathways, not along the conduit of the deep western boundary current. Because floats are very limited in number because of cost, this study was complemented with a study of the E-floats, where these floats were launched within the flame model, again at 700 meters depth and 1,500 meters depth. They were used initially just to replicate the observational study, but then we were able to integrate them, of course, much longer than a numerical model. And so the top panel on the right-hand side shows in gray the RAFOS floats, and in red and blue the E-floats, all integrated for 2 years. And we did a number of statistical studies to make sure that these floats had the same statistical coverage as the RAFOS floats. And then we were able to look at 10 years after launch what these trajectories looked like. And so overall, this study gave us an appreciation for how the waters were carried in that lower limb. So rather than thinking of the deep western boundary current as the conduit, we knew the deep western boundary current as a conduit for the transport of waters from the subpolar gyre to the subtropical gyre. Earlier work that I had done looked into the dynamics that could explain that interior pathway, and in brief, there are eddy-driven recirculations at depth that are the result of the instabilities of the Gulf Stream and North Atlantic current that drive an eddy-driven recirculation that is allowing for those interior circulations, or interior pathways. So our observational study had been done on Labrador seawater, but we were also interested whether the overflow waters also had interior pathways. And so using the numerical model, we, at this black line, had dynamic launches of both Labrador seawater and overflow water. So in the lower panel, you're looking at the cross-section at 53 degrees north, and the contours are of the velocity field, mean velocity field, and then in red is showing the launch positions for the Labrador seawater and for the in blue for the overflow water. So in this numerical model, we had what we call dynamic launches. So we launched wherever, whenever the flow at that launch site was southward, and where it met the temperature criteria for Labrador seawater, overflow water, we tagged it as either one of those water masses. And so then integrating for 50 years, we constructed those maps that you see at the top of Labrador seawater and overflow water. And so you see some characteristics, and I'll talk a little bit later about this, the spread of Labrador seawater. But right now, what I want to draw your attention to the fact is the overflow waters as well essentially are not showing that there's a single conduit of these waters along the deep western boundary current, but that there are interior pathways. Interestingly, though, when you get down below about 28 or 26 north and on down, to the tropical Atlantic, there's a convergence of those waters again into a deep western boundary current because you're moving out of that region where you have those eddy-driven recirculations. So there we recover an area where we have more of the deep western boundary current as being the primary conduit. next I want to talk about the surface limb of the AMOC. And so I'm showing here a schematic that was put together by Dave Frantoni 14 years ago now. And so Dave had took all of the surface drifter data in the North Atlantic that had been accumulated in the decade before, 1900 to 2000. So these are satellite-tracked drifters. And from that, these again are surface currents, and from that produced this schematic. And what is produced is what people have thought of for many years, showing the throughput there, following the red line through the Florida Strait, up through the Gulf Stream, on into the NAC. This red line traced along the surface flow our expectations for the pathway of the upper limb of the overturning circulation. And that upper limb of the overturning circulation has long been the sea surface, the warm sea surface temperatures in the subpolar North Atlantic relative to the colder waters off the Labrador and Newfoundland coast. Those warmer waters have long been attributed to this advection of the warm surface waters from the subtropics. This was first noted by Matthew Fontaine Murray, who was the U.S. naval officer and oceanographer. It may have been noted by Europeans as well, but at least this is what we're taught in our U.S. history books about that sea surface temperature. And so those warm waters have long been thought to be part of this overturning circulation. This whole thinking about why Europe and British Isles are warmer has come under some revamping, and so in recent years, and so the general consensus is merely that those sea surface temperatures on long time scales are the result of ocean heat advection, but on shorter time scales, the atmospheric forcing and radiative forcing plays a larger role. If you are interested in knowing more about the sea surface temperature, the surface air temperatures and their variability on interannual time scales, you might want to read a recent article by Yamamoto et al. That just appeared in Climate Dynamics. Here, thinking about this sea surface temperature, oceanographers have long associated this with the movement of heat on the surface. And so I'm showing here a figure from Sutton and Allen from 1997, where this was using not satellite data, but they used historical hydrographic data. And what they wanted to understand is how sea surface temperature anomalies propagated from the subtropics to the subpolar. And so what is shown in this plot is in year 0, they looked at temperature anomalies off the Hatteras. So they had an area called the vicinity of Cape Hatteras. And from the time series in all of these 1 degree by 1 degree bends over the North Atlantic, then they looked at the correlation and lagged correlation between the sea surface temperature anomalies off the vicinity of Cape Hatteras with the rest of the North Atlantic. And so where you see the solid circle that says year 0, and within that area is the area where those sea surface temperature anomalies are correlated with the sea surface temperature anomalies off Cape Hatteras. And so then moving on, 1 year lag, 2 year lag, 3 year lag, you can see then the area of correlation for those sea surface temperature anomalies. And so from this, Sutton and Allen we're showing that there are sea surface temperature anomalies along the path of the Gulf Stream to the North Atlantic current. So it's consistent with the expectation that we are moving, that this throughput is moving heat from the subtropics to the subpolar along that surface pathway. So understanding, though, this surface pathway started to have some cracks in it, though, with a very interesting study by Elena Brambell and Lynn Talley a decade ago. So if you look on the left, the same drifter data that David Frantoni was using. This is from 1990 to 2002, and took all of that surface drifter data and basically then averaged it. So used it in a quasi-Eulerian sense. And when you look at that surface velocity map that results, The red arrows are showing you the strong velocities greater than 20 centimeters per second, and the blue arrows are the much weaker velocity fields. But what you see is pretty much what we saw earlier in Frattantoni's schematic, that you can trace the strong flow through the Florida Straits, up off Cape Hatteras, and then you can see it moving on into the North Atlantic current, and so we see a surface throughput. However, when Brambill and Talley then actually looked at the floats, the drifters themselves, on the right-hand side, everywhere you see a gray asterisk were the deployments that were south of 45 degrees north, and then you see that there is one drifter that ended up north of 45 degrees north. And so Brambill and Talley, its lack of exchange to a number of things. Perhaps there was a limited drifter lifetime. Perhaps there's temporal variability in throughput. So over these years that they were studying this, 1990 to 2002, perhaps there was very little throughput. And then they also mentioned that restricted exchange could be due to the fact that the drifters are restricted to 2D flow. So I was very interested in this and had a student, Christy Burkholder, work on this while she was here with me at Duke. And what you're seeing in this slide here are drifters within the flame model. So these, again, are virtual drifters. And what we were testing here is longer lifetime. So these now are 4 years. I don't know if I mentioned it, but the average lifetime for the drifters was 270 days for the observed drifters. So what we did here is we took the same observational launch points as the surface drifters and used those in the model, restricted the flow to two dimensions, just as in the observational floats. But we looked at different time periods, so we have 1991 to 1995, on to the next 4-year period and the next 4-year period. And basically tried to see, well, if we integrate for a longer time or integrate at different times, can we get any throughput when launching floats at the surface and restricting them to 2D? And the answer is pretty much no, that this model is demonstrating what was observed with the surface drifters over those 12 years. Instead of looking just at the observational launch locations, what we decided to do, if you look in the lower left-hand panel, is in the model again, make sure that we're launching floats in the Gulf Stream. So we used the definition of being in subtropical waters as being in the north wall, as where the 15-degree isotherm intersected 200 meters. And we launched floats regularly, dynamically, from that position. And at this point then, we used the 3-dimensional velocity field and integrated for 4 years. And so what you see on the right is a plot of the percentage of floats reaching 53 degrees north as a function of their launch depth, and plotted in the dark blue curve. And what you see is that there are very few floats that reach 53 degrees north that are launched near the surface. You maximize the fraction of floats that reach 50 degrees north at about 700 meters. The other thing we tracked is the change in depth of these floats. So from their launch depth, they essentially ride up the isopycnals to the subpolar gyre, so that floats that are launched at about 300 meters, etc., are the ones that end up near the surface. And so this is illustrated in this next plot. So in addition to doing forward trajectories, we were interested in doing backward trajectories. So we went to where we have these really warm surface waters in the eastern subpolar gyre and asked, what's the source of these waters? These are the waters, again, that we believe have their origin in the subtropical gyre, and we had believed that that origin was largely the surface waters in the subtropical gyre. But by running these trajectories backwards for 4 years from that eastern subpolar gyre, in the context of this model, we found that their initial locations are they come from depth, from 200 and 300 meters in the subtropical gyre. So the majority of the waters are coming from the subtropics, but they're not coming from the surface waters. So you can see on the bottom panel, whether we reduce them at 5 meters or 50 meters or 100 meters, 70 to 80% of the waters have a subtropical origin. And are coming at depths of 200 to 300 meters in the subtropics. This is the depth of the subtropical mold water in the North Atlantic. That in just a moment. So, do we have observational evidence of this? We don't have a lot of observational evidence of this, primarily because we don't have a lot of Lagrangian data in the North Atlantic, particularly Lagrangian data that can track these new surface waters. But there are some hints. So I'm showing here some information from Frattantoni et al. 2010-2013, which are results from the Climate program. And Dave and colleagues released these bobber trajectories that were tracking the subtropical mold waters. So these bobbers bob between the isotherms that define the subtropical mold water. And what you can see, the yellow are where these bobbers were first lined, where the upper left-hand panel is showing the trajectories, and many of them you see, of course, are recirculating in the subtropical gyre. But there are some that show this very nice throughput from the subtropical to subpolar. And you can see then in the bottom panel a subtropical to subpolar ascent of these bobbers. So they are essentially riding up, as we're just looking at the background isotherms in that lower right-hand panel as well. And so as those parcels are moving, they're staying within their the isotherms as programmed, but you can see that they are moving into the subpolar gyre and rising in depth accordingly. So we have proposed that a revision of the surface throughput, rather than the model that result from analysis of the surface drifters, we have proposed that instead the waters that get to the eastern subpolar gyre, that's surface waters, really have their origin from depth in the Gulf Stream, and that's the depth of the subtropical mold water. So this is a very, very simplistic schematic you're seeing in the lower left-hand corner. But what we're proposing is that the waters, when those warm Gulf Stream waters are really, we know that they are transformed by the buoyancy forcing, and there's this strong formation of the subtropical mold water every winter. Those waters are subducted to depth. And those waters have a recirculation timescale of 3 to 4 years in the subtropical gyre. And so what we're proposing is that those waters then have the density characteristics then that be in the surface waters of the subtropical gyre. So it appears to us that it is those waters at depth that are providing the surface waters in the eastern subpolar gyre. So leads to questions that a current PhD student of mine, Nick Focal, is currently exploring, which is what is the time scale for the thermal and hailing anomalies in the subtropical gyre to reach the subpolar gyre? How does the local buoyancy forcing in the subtropical gyre, and then the magnitude of these anomalies? And what is the variability in the throughput? I should say quickly is that for many years we've thought about in the Labrador Sea that the convective process that's taking place there is really the producing the end product, like the Labrador Sea waters, the end product of the convection that's been taking place all along the pathway in the subpolar gyre. And what I'm suggesting here is that this warm water throughput that we have also has some is experiencing buoyancy forcing in the subtropical gyre. And that's going to amend its temperature and salinity properties as well. So rather than just thinking that we've got this transformation that's taking place in the subpolar gyre, that transformation, I think, is starting to take place, in that vicinity of the Gulf Stream, where there's very, very strong sea exchange. Okay, so let me move on to. I'll go quickly through this, but this, Bingham et al., this paper, and it appeared in 2007, really our mind quite a bit about the character of the AMOC. I think it's safe to say that prior to this, people had the expectation that there was an AMOC, and we just needed to measure one place, and we would know what that measure was. But this work did a great job of helping us understand the meridional coherence of these overturning circulation anomalies. So what you're seeing on the left-hand side is the results from an atmosphere-ocean climate-coupled model, and on the right-hand side is from an ocean-only model. The upper panels are showing the mean overturning, and the lower panels are showing the MOC anomalies. So this is a Hofmuller plot. And what I primarily want to draw your attention to is the lower right-hand panel that shows a break in the coherence of the anomalies at about 40 degrees north, which is about the what we consider the latitudinal divide between the subpolar gyre and the subtropical gyre. So this paper started really a number of people looking at the question of not only meridional coherence in the MOC, but in the heat transport as well. And people were trying to understand it mechanistically. Shortly after that, Arnie Biestock and colleagues put out a paper that's based on modeling results, where that looked at two different models, one with interannually varying buoyancy forcing and climatological winds, other with that varying buoyancy forcing and interannually varying winds. And so in both of these models on the upper panel, you're looking at the change in the Labrador seawater formation rate. Red shading indicates periods in both models where there were high volumes of Labrador seawater formed. The green bars indicate positive NAO periods. And what you see is when you're using climatological winds, what Arnie was showing was that there was a strong penetration of the AMOC anomalies from latitudes to the low latitudes. But when interannually varying winds were introduced, that meridional coherence was really disrupted. So this really started an investigation into the impact of the wind forcing compared to the buoyancy forcing on the AMOC and its temporal variability and also its meridional coherence. The last thing I want to get to here is the question that really is forming the basis for our OSNAP study, and is our changes in convective activity in Labrador Nordic seas manifest in a temporally variable meridional overturning circulation. So I do not have time to do this here, but I think many of you know that model after model have demonstrated that the changes in acidity and temperature at high latitudes are manifest then in a change in the production of these water masses, which then are manifest in a change in the overturning circulation itself, which then result in changes in the sea surface temperatures in the North Atlantic. And the IPCC fifth assessment shows that in all models shows a slowdown into the 21st century of the overturning circulation, and the mechanism that's responsible for producing that slowdown is a change in the production of the high latitude water masses. What I just wanted to talk about here is what's the observational basis, for this linkage. And I'm going to there's a lot of studies here. I'm just going to show a few, and one that was particularly illustrative was a Fisher et al. Study, and this was based on analysis of waterways and hydrographic sections that were taken over a 15-year period or so, almost a 20-year period, in the Labrador Basin. And so you're seeing in the left-hand panel a schematic showing where those arrays and sections have been. And then in the lower right-hand panel, you're looking from 1996 to 2009, the time series of particularly the Labrador seawater at all these different locations. And so over this time period, you see there's been a general warming of the Labrador seawater at these different locations. Our expectations years ago would have been that if there's a warming of the Labrador seawater, we would have had in its export, and that we would have thought would have been a reduction in the deep western boundary current. In the top panel, though, from all the different moorings this is mooring K9, from 200 meters to 2,800 meters, and the other moorings are the same thing, that there has been really no change. today, though, thanks to many people's work, we could say, well, why don't we see that observational linkage between a change in the amount of Labrador seawater that's being formed and the deep western boundary current? We know now deep western boundary current variability is not synonymous with overturning variability. So what they were measuring was the deep western boundary current, and so that's not the same. But the other thing we know is that the water mass variability in the boundary current is not solely the result of convective overturning in the Labrador Basin. And we have a study that FIAMA put out in 2006 that really, to me, was very instrumental in changing our view of what's impacting both the properties and the transport that are being exported from the Labrador Sea. So when I was a graduate student many years ago, we understood that the heat loss from the ocean, that buoyancy loss in the Labrador Sea produced a water mass, and that volume of water was directly related to the amount of heat that was lost, and that volume then would be added to the overflow water volume, and that would produce our AMOC. So FIAMA, the schematic that's showing on the left, FIAMA, illustrated that we can think of the interior of a convective basin like the Labrador Basin as having exchange with the atmosphere, and there can be that buoyancy loss that produces a thick mass of this convective water, but it is interacting through an eddy exchange with a wind-driven boundary current. And so we see then that the boundary current has light water on top, a smaller volume of dense water when it's going in, and then there's a transformation of those waters, and many of those lighter waters are transformed to denser waters, so that when the waters come out, they take on the properties of what we call Labrador seawater, but it's really through the eddy exchange. And so when the waters are exported from a convective basin, and we can think of the Labrador Sea Basin here, that volume and the properties of what's exported is the result of a number of things: the strength of the eddy exchange, the strength of the boundary current, the properties initially of the boundary current, as well as the exchange across the air-sea surface in the interior. So Jamie Palter, who's also on the line when she was here working with me, looked at a study using the Pallas floats and looked at how that flow from the Labrador Sea was exported. And as part of that was looking at the exchange by eddies. And from that study also showed that there were very strong down gradient eddy fluxes from the boundary current into the interior, which is providing some observational evidence for what FIAMA was suggesting in this study. I think the work by the FIAMA and then also Bob Tickart and Mike Spa really did a lot to change our understanding of these water masses and their connection to what we call the overturning. So I just wanted to say another student who's working with me now, Sajia Zhao, is working on this question about the Labrador seawater. So earlier, I just said that we don't really expect the Labrador seawater that's formed in the basin then to all be in the deep western boundary current and then exported. And so prior studies that I mentioned that Amy Bauer and I had done with the observational floats, and prior studies that had been looking at this question of export always released everything in the deep western boundary current. And so Sajia just produced this a few months ago, where we looked at recently formed Labrador seawater at the end of one winter. This was along the AR7 West line in the context of the ORCA model, and then marked where all this very low PV water was, and then basically integrated forward for 40 years. And what you see is that newly formed Labrador seawater, most of it is actually still in the Labrador seawater after 40 years, and there is almost a diffusive exchange. I'm going to call it, it looks like a diffusive exchange across that subtropical subpolar boundary. So observational studies, modeling studies are really changing our understanding of the pathways of how these deep water masses are moving from the basin to the other, and gives us, I think, a greater appreciation for what we're really looking at when we're measuring the properties and transports of these deep western boundary currents. I'll mention briefly, because I'm afraid I'm going to run out of time here, is that this is courtesy of Kirsten Jokenberg, and so through the NACLIM program, they've been monitoring the flows through mooring arrays across the Denmark Strait. And I will say that a study, the Jochumsen et al. 2012, shows that there has really been no trend in transport over the years 1998 to 2012, even though there has been some warming, and then that warming stabilized at the sill and then further downstream at Amosalik. So we are, I think, still, you know, it's unclear what the relationship is between the property variabilities that we're seeing and the transport variabilities of the water masses, and then how that feeds into our total measure of the AMOC downstream. Where are we? The linkage between convective activity and AMOC transport variability and observations has been elusive. I think in the long term, when we're thinking about climate change, we're expecting warming and freshwater changes to continue, or expect warming and freshwater at high latitudes to continue, both in the direction of stabilizing the surface waters. So this prompted us to, several years ago now, initiate a program called OSNAP. This is a US-led program with contributions from UK, Germany, Netherlands, France, Canada, and China. So this array was meant in large part to complement the rapid array, because we have had this understanding that there are different measures of the overturning in these basins, but in large part the OSNAP array is really, its main purpose is to answer the question about what is the relationship between mass production and AMOC variability. And that is the question in addition to monitoring these flows. And so in order to do that, we have arrays on both sides of the basin, and then we have mooring arrays on both sides of the Erminger Iceland Basin. There's a glider survey in the Rockall Trough of the Hutton Plateau thing, and then there's a mooring array on the Scottish Shelf. There's a glider survey that the UK is providing. Another glider survey will start this summer that Ocean University of China is conducting. And complementing this program is a float program that Amy Bauer and I are conducting. And the purpose of that is to look at the Lagrangian pathways of the overflow waters. And we're interested in those pathways in general because we want to know how they're exported to subtropical gyre. But these Lagrangian pathways are also going to help us interpret what we're seeing moving through each of these arrays. Just give a summary, because I do want to leave some time for questions. What I think I'll do, I think I'm just going to leave this summary slide up here and ask for questions and just go to this unaddressed lingering question. To me, one of the most important questions we're still trying to figure out now is the impact of AMOC variability on SSTs. There are many studies, observational modeling, that stress the importance of SSTs for a whole host of things: continental precipitation, atmospheric temperatures, hurricane activity, etc. But the AMOC variability on SSTs and the time scale in which that is important, I think, is still an open question. But the more we understand about the transport of the AMOC, its variability and its structure, I think the closer we'll get to answering that question. I have just breezed through this, and I hope I have given enough time here for people to send in questions. So